So what is sampling? Heuristically speaking, it is the operation or process through which continuous time signals are converted into discrete time signals. The idea is that a continuous time signal consists of an infinite number of values, and you want to reduce that to a discrete set of values. The process by which you take that infinitely continuous number of values into a discrete set of values, that's called the sampling operation. Now that sampling happens in different systems in different fashions. For example, the way your voice is sampled into a digital wave file or MP3 is different from the way your body's is sampled through an MRI machine. Okay? It is still called the sampling operation, but the process is different. The mathematical expressions are different. So in this class, we'll only talk about the most fundamental or basic form of sampling, which is called basic, and it's also simplest, which is uniform pointwise sampling. So what is uniform sampling? Uniform means that it considers the signal, and it doesn't matter where the signal is, it's doing the same operation at a uniform rate. Okay. So pointwise, basically what happens is that after every few seconds, and the seconds could have any unit, so it could be millisecond, it could be a microsecond, it could be a nanosecond. We record what the value of the continuous time signal is. And we put it in a sequence. So imagine this is your continuous time signal x of t. This is your time t. Okay. And let's say this is t equal to 0. What pointwise sampling does is, let's say you start the sampling operation at t equal to some minus 200 seconds, right? So you start the sampling process here. This is, let's say, t equal to some number minus 2 capital T, where capital T could be, capital T is, let's say, 100 seconds. Right? So what happens is you go in time and you figure out what is the value of the signal at that particular time. And you record that. Then you wait another t seconds, and then you again go in time. So this is t equal to minus t. And you record the value. You go then to next t second, you record the value. And you keep on doing that process. So this is t equal to 1, t equal to 2, t equal to 3, 1t, 2t, 3t. And this is t equal to 4t and 5t. And then you just collect that in a sequence. So you call this x of minus 2. This is x of minus 1. This is x of 0. x of 1, this is x of 2, this is x of 3, and so forth. And then you forget that you ever had a continuous time signal. You just keep your sequence in with you. So at the end of the day, what you will end up getting is a sequence which will be x of -2, x of -1, x of 0, x of 1, x of 2, and so forth. So why is it called uniform? Because you go to your continuous time signal, you sort of probe your continuous time signal every t seconds. This gap is always t seconds, so that's the uniform part. Okay. You can have non-uniform sampling too. We won't cover that in this class. Now, once you access your signal every t seconds, it's like your hardware circuit sort of ignores whatever I am saying for t seconds. Let's say that t is 1 microsecond. And then every 1 microsecond, it starts looking at what was I saying. Now, every t seconds, then it goes and looks at it at that particular point in time. So that's the point-wise sampling aspect. You only look at what is the value at that time. You don't care what is happening around it. Okay? So the uniform point-wise sampling with time period of t seconds, it's often written as you have x of n, and that x of n corresponds to samples of your continuous time signal every t seconds. So you write it like this, or effectively you are looking at x of t where t equals to nt. So the nth sample is nothing but the value of your function at nt seconds. The 100th sample is whatever your signal was at 100 times the t seconds. So if t is 1 second, that's x100 is what my signal was at 100 seconds. Now, in the language of sampling theory, this t is called the sampling period. And using this t, we can define f equal to 1 over t, which is called the sampling frequency in hertz. Some people write also fs to signify that this is the sampling frequency. And then you can also express that in radians per second. So that's 2 pi over t or 2 pi f. So this is sampling frequency in radians per second. So when you restrict yourself to uniform pointwise sampling, that's the way you go from continuous time signals to discrete time signals. There are still a couple of questions that you have to ask. So even within that context, the first question you have to ask is, under what conditions on x of t and t slash fs slash omega s, you could be given any number, is sampling a process that loses no information. Can I sample any signal or using this process? Can I use any value of capital T? Is T 100 seconds good or is T 100 microseconds good? The second question is, once you have sampled it, in many cases, you also want to recover the original signal. You record a song, you want to listen to the song again. Now, your recording is discrete time, you want to convert that back to continuous time. So the question becomes how to recover x of t from its samples xn, assuming that there was no loss of information in the first part. So we'll understand the conditions on x of t and the time duration. So let's look at the conditions on x of t. Again, this is a topic that could be a class in its own right, because you can look at many different types of signals. In this class, we'll focus on one type of signal only, which is very common, that the signal to be sampled is band limited. What is band limited means that there are no frequencies present in the signal above certain value. Let's call that omega m radians per second. So band limited means your signal, or if you want to talk about in hertz, there is a certain value in hertz beyond which your signal has no frequency present. So that will be the type of signals we'll be interested in. And why band limited? Because if we say that our signal has no frequency higher than, let's say, 1 kilohertz or 1 megahertz, the question is that in that case, what does it mean about the signal? Why can we then sample that signal easily, perhaps? If you say that there are no frequencies present above omega m radians per second, or let's call it FP hertz, FM hertz, right, which is omega m over 2 pi hertz. This means that there is a maximum rate at which your signal can fluctuate, and beyond that, your signal is not fluctuating very highly. And if things are not fluctuating very highly, then somehow the notion is that you can capture that information easily. Right? If your signal wasn't band limited, if it had infinite number of frequencies, then the signal could fluctuate at such a high rate that there is no way you could ever capture information in that signal. Right? If it had, you say, well, maybe the signal has 1 gigahertz frequency, but someone says, no, it's not limited there. It could even have 10 gigahertz. It's now fluctuating so fast, it keeps on fluctuating high, because frequencies means the rate of change, that you cannot capture that signal in discrete time. It's sort of that intuition. So this is the highest rate, and the signal has no fluctuations that faster. And when I use the word fluctuation, I'm not using it in a very rigorous sense, right? The general idea is frequency means the rate of change. How the fluctuation will look like is different. So if you have a stock price which is really going up and down, you know that its highest frequency is pretty high. So the signal has no fluctuations beyond this limit. Now, since we have done the continuous time Fourier transform, we can also put this notion of band limited signal in a rigorous manner, we can say, so what tells us whether the frequencies are present in the signal or not is the continuous time Fourier transform. So I have a signal x of t, let's say, and I compute its Fourier transform x of j omega. And if x of j omega equals to 0 for all omega frequencies bigger than or equal to omega m radians per second. So your Fourier transform, if you're saying it has no high frequencies present, then your Fourier transform must be 0 beyond that point. And so that's the mathematical definition, that if your x of j omega equals to 0, then you say that x of t is band limited to omega m over 2 pi hertz, or omega m radians per second. So a Fourier transform, here are some examples. If I have a Fourier transform like this, I plot just the magnitude. This is minus 2 pi 10 to the 3, 2 pi 10 to the 3. So is this signal, so this corresponds to some signal x of t, is this signal band limited or not? So this is a band limited signal with 1 kilohertz maximum frequency, or since it's a real value, the frequency is the same, it's symmetric around 0, so I can just talk about 1 kilohertz. Now here is, you take your signal and you compute its Fourier transform, and it looks like this. So is this a band limited signal or not? To make it clear, what this picture says is that this continues forever like this. So this signal is not band limited because it doesn't, first of all, become 0, but even if it became 0, it doesn't stay 0. Here is another example, which, just to clarify, another signal which could be, let's say, exactly like this, but then it became 0 for a little while. And then it became non-zero. Even this signal is not band limited. Even though it became 0, it doesn't stay 0 forever. Now here is a third example, which is really what happens in reality. A signal which is like this. It is going to 0. It probably never touches exactly 0, but it has gone down so far. The high frequencies are have so little contribution that we say that this is approximately band limited. So this is approximately band limited. And the bandwidth of these kinds of signals is determined by the nature of the application. There are different definitions of bandwidth. There is something called 3 dB bandwidth, which is the point at which your signal, the frequencies, you look at the Fourier transform, and the highest point has dropped to its 50% peak value, right? There are many other definitions, or sometimes it's just a sense of, well, what does band limited mean in terms of what is the critical information available in that signal. But for all practical purposes, this kind of a signal will be considered band limited. So as an engineer, what you should keep in mind is that real world signals are never exactly band limited, but they can be perfectly approximated because of the operational needs using band limited signals. The classical example of that is, of course, music. You could generate sounds which go above 20 kilohertz. But human ears, unless you are designing a music player for another species, human ears cannot hear anything above 20 kilohertz. It's been, no, regardless of what people tell you, it's not going to matter whether your song has the frequency 25 kilohertz present in it or not. And if that is the case, for all practical purposes, we can say, well, my music is band limited to 20 kilohertz. And then I treat it as a band limited signal with the right modifications that I need to make sure it indeed acts as a band limited signal. So why are we caring about band limited signals? The idea is that if signals are band limited, then they can be sampled without loss of information. So then the question becomes, we already talked about the condition on the signal, then how should we select T sampling period or sampling frequency, whichever one you want to talk about? And the answer depends upon the signal bandwidth. And that is where domain knowledge comes into the picture. You really have to understand what are the characteristics of the problem that you are dealing with. So here are some examples. If you are talking on a landline telephone or even, let's say, cell phone, for all intensive purposes, people have determined that to make intelligible conversation, the information is contained in the first 3.4 kilohertz of your speech. Even though when we speak, we have higher frequencies, to make our conversation understandable, it's enough to just capture the 3.4 kilohertz, the first 3.4 kilohertz of that speech. So if you are transmitting over this copper wire, you can consider your signal to be band limited to 3.4 kilohertz. And that is one of the reasons that when you hear people on the phone, they sound different than when you hear them in person, because you are throwing away their higher frequencies. Now, HD video, the high definition video, which tries to preserve HD voice, which tries to preserve more of your higher frequencies, the definition of that is determined by that 7 kilohertz. So The idea is that in 7 kilohertz, you capture now most of the information in your voice, but you may, especially if you are singing, that's why you don't want to compete on American Idol by singing on the phone. Not a good idea, right? Because they won't be able to listen to your higher tones. And if you really want to talk about, crystal clear sound exactly like what you sound, then that's called, in the modern lingo, that's called the full HD voice. And that goes up to 20 kilohertz. And the reason for that is, as we talked about, human ears are not very sensitive to frequencies above 20 kilohertz. So what bandwidth to consider for the signal depends upon the application that you have in mind. If you are running a song contest over, let's say, in a remote fashion, then you want to consider it to be a 20 kilohertz bandwidth signal. Now, here is an example of an ECG signal for which the bandwidth is a completely different unit. It's not even in kilohertz. It's only in hertz. For most practical purposes, an ECG signal can be considered as band limited to 150 hertz. At least the typical ECG signals, which are not showing any major variations. Now, again, to know that, you will have to have some domain knowledge. The last example is we can think of seismic traces, which measure the activity in the Earth's core. And again, the bandwidth of these signals is really low. Typically, that's around band limited to around 125 hertz. So it's really a question of which application you are dealing with. There is no universal number that sampling means take the bandwidth of the signal to be these many hertz. You have to understand the application, and then you have to use domain knowledge to come up with a reasonable number for the bandwidth. So then we say, well, we need band limited signals. The bandwidth of our signal is now fixed by whatever application we were dealing with. Then what is the role of sampling time? And when I say sampling time, I can use that term or sampling frequency in hertz or radians per second. They all mean the same thing because they are interchangeable. And why is that important? You can't use any sampling time. And one of the fundamental reasons for that is that if you think about it intuitively, continuous time frequencies range from -infinity to infinity. Whereas discrete time frequencies fundamentally they range from -pi to pi. After that, they just repeat themselves. So one sampling time, a fixed sampling time, cannot be appropriate for signals of all possible bandwidths. The sampling time that you want to use for an ECG signal is not appropriate for an HD voice signal. And the reason for that is that you always have some ambiguity, which we'll discuss more formally. There is always an ambiguity in going in going from continuous time to discrete time. So we'll look at it with a very simple example. We'll do a formal discussion of sampling theorem later, but the example is that of a pure cosine signal. So it's example 2.5 in your text. So let's say you are given three signals. G1 of t is cosine of 6 pi t. G2 of t is cosine of 14 pi of t. And G3 of t is cosine of 26 pi of t. So the first signal has frequency 3 Hertz. The second signal has frequency 7 Hertz. The third signal has frequency 13 Hertz. And you decide to sample all of them. Sample each one of them using a fixed sampling time. Using t equal to 0.1 seconds, which means that your sampling frequency is 10 Hertz. So you are using a 10 Hertz sampling frequency to sample all three of them. So using the notation G1 of n is going to be G1 of n capital T. So I just put that in 6 pi times nt. That will be cosine of 0.6 pi n. So you sample a continuous time cosine, you get a discrete time cosine, and the frequency of this discrete time cosine is 0.6 pi. Okay, let's do that now for the second signal, G2n, which is simply samples of your continuous time signal every t seconds, which is cosine of 14 pi times nt, which is cosine of 1.4 pi n. Now, using the understanding that our fundamental frequencies are between minus pi and pi, what does 1.4 pi frequency mean in terms of the fundamental frequency range? So to compute the frequency in the fundamental range, you do 1.4 pi minus 2 pi because it's in the second part of that repetition. That's negative 0.6 pi. So I can write my G2n equals to cosine of 0.6 pi n. Now cosine of minus x is the same as cosine of x. So that is equal to cosine of 0.6 pi n. So what do I see here? That even my second signal, I sampled my second sinusoid, continuous time, and I get a discrete time cosine, but the frequency of that discrete time cosine is also 0.6 pi. Even that continuous time signals had different frequencies. One was 3 Hertz, one was 7 Hertz. When I converted them to discrete time, both of them have the same frequency. Let's look at the third case. G3 of n is G3 of nt, cosine of 26 pi times nt. That's cosine of 2.6 pi n. Again, this is above the minus pi to pi range. If I bring it back to minus pi to pi range, I do the same thing, 2.6 pi minus 2 pi. So that's 0.6 pi. So this means that G3 of n is equal to cosine of 0.6 pi n, which means the frequency of that is 0.6 pi. So what we see here is that we started with three different continuous time cosines. But when we used the same sampling period for those three cosines, we got back the same discrete time signal. Now, if someone were to show you that discrete time signal and ask you, where did it come from? You cannot tell them apart. You can't say, if I just showed you a sequence of cosine of 0.6 pi n, you cannot tell me whether the original continuous time signal was a 3 hertz frequency or a 7 hertz frequency or a 13 hertz frequency. So this is the ambiguity that is inherent in the sampling process. All three signals get mapped to the same discrete time signal. And the reason for that is that the choice of our frequency of sampling frequency of 10 hertz. Okay. Once we have cosine of 0.6 pi n, we cannot know whether the continuous time signal was 3 hertz, 7 hertz, or 13 hertz. Okay. And this is the fundamental issue in sampling theory, the ambiguity that arises. This is a pictorial representation to convince you that indeed what you are seeing mathematically is true if you do MATLAB and do the three frequencies. So here you see three frequencies. One is slower, 3 hertz, the other is a little faster, 7 hertz, the other is even faster, 13 hertz. But when you start taking samples of those, the samples all correspond to the same values. So now if I take away the background 3 cosines, you have the same sample values for all of them, and you don't really know where those samples came from. So in most cases, then what happens is in sampling theory, since you cannot tell them apart, you say, well, I'll use the lowest possible frequency that describes my samples. Okay. So in the signal processing literature, you often do is you use the lowest possible frequency, the continuous time frequency, to describe the discrete time signal. Now, right now you don't know, but the reality is that there is no frequency below 3 hertz that actually describes that discrete time cosine of 0.6 pi n. There is no continuous time frequency lower than that. So what happens is whenever you see cosine of 0.6 pi n, you will say that my original signal is a 3 hertz signal, even if the original signal was a 7 hertz or a 13 hertz signal. It is like, for the 7 hertz and 13 hertz, it's like 7 hertz and 13 hertz take the identity of the 3 hertz signal. And in the real world, when you take an additional identity, we use the term alias with that. That someone's name is this, alias this. So this phenomenon is actually in signal processing literature is called aliasing, which we'll study in a more rigorous fashion later, is the phenomenon of higher frequencies getting mapped to the lower frequencies once they are sampled. Aliasing is a big concern in sampling theory, which, as I said, we'll look at it later in more detail. But the whole issue of figuring out what time period to use for sampling is determined by how do you avoid aliasing. If you know that you are going to get continuous time frequencies up to 13 hertz, then you better use a time period that makes sure that 13 hertz never gets aliased to a smaller frequency. Right? So for every time period, there is a maximum frequency beyond which any higher frequency in the signal will get mapped to a smaller frequency.